All right, a very quick polar review because we've actually reviewed polars once already, and I want to make sure that we dive into the derivatives with polar. Polar review, very similar to parametrics. The difference here is, whoops, again, man, typos all over the place. Dependent variable is R. Um, Independent variable is theta, an angle that is measured from the positive x-axis counterclockwise around the origin. And the dependent variable is r, which is the radius, just like in a circle. So we're actually measuring angles in radii. We are still graphing on the xy plane, however. And much like with parametric, the whole idea of this is it's not just the shape we want, even though this is a great way to be graphing non-functions, especially things like circles and ellipses and more advanced shapes like cardioids and flowers, or roses is the technical term we would say, um, and limicons and all of those fun shapes. But we want to see the order we're graphing these. So an example of this would be r equals the cosine of 4 theta. So if theta is 0, if theta is 0, I would plug 0 in for theta. Cosine 4 times 0 is 0. Cosine of that is 1. So r would be 1 when theta is 0. So here is where my point would be. If I had, say, pi over 4, I'd have 4 times pi over 4, which is pi. Cosine of that is negative 1. So when the angle is pi over 4, I have to go backwards 1. Then, if I have pi over 2, I'd have cosine of 2 pi, which is 0. So what I actually get is I'm going to have something that is going to end up going around, oops, like this. But it's the whole idea of I can graph this by plugging in different thetas, finding out what the radius is, and plotting those points. To graph these, we basically want to turn them into parametrics and then treat them like a parametric. So we start by just changing the polar into rectangular form. So to get the x equation, I take whatever r is times cosine of theta. To get the y, I take whatever r is times sine of theta. And then, much like with parametrics, because we are on the xy plane, my derivative has got to be dy dx. But since x and y are now written in terms of theta, I would do dy d theta divided by dx d theta. And again, it's easiest to see this with an example. So if r is equal to 4 sine theta, I need to figure out x and y. So x is going to be r times cosine of theta, but r is equal to 4 sine theta. So my x is 4 sine theta cosine theta. My y is going to be whatever r is times the sine of theta, but r is 4 sine theta times another sine theta. So I'm just going to say that y is equal to 4 times the sine of theta all squared. Well, just the sine is being squared. So now if I want the derivative, I need dy d theta. So the derivative of y with respect to theta. This is going to be a chain rule problem, so I'm going to take care of the squaring first. Times the derivative of sine. And there is my dy d theta. So for dy dx being equal to dy d theta over dx d theta, dy d theta is the 8 sine of theta cosine of theta. Then I need dx d theta. And to do this, I'm going to need to do product rule because I have sine of theta times cosine of theta. I'm going to treat 4 sine theta all as the first term. So I have first times derivative of second plus the second times the derivative of the first, which if I clean that up gives me negative 4 sine squared theta plus 4 cosine squared theta. And I can replace my dx d theta in the denominator with that. And here is my derivative for this polar function.